Hello, AP Stat students. Today we are going to learn about linear regression and finding an equation for the line that best fits our data using our calculator. So first, let's review what we've learned so far. It says use the data below to see if there's an association between the number of houses a trick-or-treater goes to and the number of pieces of candy they receive. 8 trick-or-treaters were sampled on Halloween and the results are below. So I said make a scatter plot using your calculator, sketch it below. So you can see there's houses and candy. So obviously when we're making a graph, the houses will be the explanatory variable, or the x, and the piece of candy will be the y, because you have to go to the house before you can get some candy, so the house comes first. Doing that in your calculator, you get this screen over here. But notice I said sketch this below. And you don't have to make a perfect graph when you're making a sketch of a scatter plot, but you should do a couple things. You should label the x-axis as houses, the y-axis as pieces of candy. And then all we need is just a quick sketch. Doesn't have to be perfect. It's just kind of relative. Okay, I can tell by that picture that you did it on your calculator, and that you have kind of an accurate picture. So when I say sketch, that's what we're talking about. Just label the x and y axis. Just draw a rough sketch. You don't have to scale the axes or anything like that. Just a quick sketch, just so we can tell you did it. Okay, and then it says interpret the scatter plot. So if you look at it, it appears that there's a relationship between the houses you visit and how much candy you get, which should make sense, I think, if you think about it. So to interpret the scatter plot, we'd say there is a strong, positive, linear relationship between houses visited and the amount of candy received. Okay, and then we should do a context statement like the more houses you visit, the more candy you get. Something like that, okay? So remember, strong positive linear relationship between houses visited and the amount of candy received. The more houses you visit, the more candy you get. Then it says, find the correlation and describe what it tells us about the association. So on our calculator, we'll find the R value, and the R value is 0.96 if you round to the hundredths place. So remember, that tells us that there is a strong positive correlation between houses visited and the amount of candy received. Okay. So when a scatter plot shows a linear relationship, we would like to summarize the overall pattern by drawing a line on the scatter plot. And I did that above already. I just sketched a line, but there's actually a way to find out exactly the line that would best fit the data. And that is called doing a linear regression. So a regression line. In general, a regression line is a line that describes how a response variable y changes as an explanatory variable x changes. We will represent the regression line with an equation in y equals mx plus b form. You recognize that, I'm sure. It's called slope-intercept form from algebra, or algebra 2. So you have experience with that kind of stuff. What we do in AP Stats is called creating a least squares regression line. Okay, there are many types of regression, but in this class, In AP Statistics, we do what's called the least squares regression line. And we use a regression line to predict the value of y for a given value of x. So the idea is once we have an equation where we know the slope and the y-intercept, then we could plug in values for x, like how many houses you visited as a trick-or-treater, and we could predict how much candy you got. So that would be the value of finding this regression line. Would allow us to make predictions. Special note here, note that regression, unlike correlation, requires an explanatory variable and a response variable. Okay? The variable we are trying to predict becomes y, and the input variable is x. That's very important. Okay? We have to have an explanatory and response variable relationship. Okay? So our least square regression line will be abbreviated LSRL, least square regression line. In statistics, it's written a little bit differently than in algebra. So you can look over here. Where B was the y-intercept in algebra, in statistics, B is the slope, okay? And then A is the y-intercept. So it's just a different way to write the equation. The number next to x in either equation, and the algebra version's over here, the number next to x is always where we put the slope, okay? And then the constant, or the number by itself, is always the y-intercept. Doesn't matter what letter we're calling it, okay? But in statistics, we do call the slope b. So the graph below, left, shows the regression line for the houses versus candy association. Okay, and I drew the line on top of the scatter plot. So notice the line passes through really close to a couple points. But in general, that line is going to average out all of the data points, okay? And this line right here is the least squares regression line. Now, notice in the scatter plot, not all the points are exactly on the line, okay? The differences between the regression line and our points are called residuals. And if you added up all the residuals, they would cancel out. And what I mean by a residual is this. Like that distance from a point to the line, the least square regression line, okay? You can think of them as kind of like they're the error statements, like how far off was the real data from our regression line. And the funny thing is, if you do add them all up, they cancel out, kind of like what happened with standard deviation. So what we do is we square them so they all become positive. So notice I made little squares on the graph. So now when I add up all those values, they will not cancel each other out. Okay? The line of the best line through the data minimizes the sum of these squares. Okay? That's why it's called the least squares regression line. Okay? You could draw other lines through this data, like let's say I drew one like this. If I figured out all the little squares, how far off every data point was, when I added them up, I would have a bigger sum than the line that was chosen, okay? So that least square regression line guarantees us that the sum of those squares is the smallest possible. So that line best represents our data. Now the good news is our calculators have a built-in function to find the least square regression line. Using our data on houses and candy from trick-or-treating, let's create a least square regression line that predicts the number of pieces of candy from how many houses we visit. So we find the equation the same way we find r on your calculator. It's in the same location, okay? If you remember from the previous lesson, we found r by doing a linear regression, while the equation part of it is just above that on the same screen. So we'd go stat, calc, and then move down to linear regression, okay? And then hit enter. And the equation we'll write will be written in y equals mx plus b form. Notice on the calculator, it called a the slope and b the y-intercept. The calculator, this is not a stats, like linear regression is not written for stats in this situation. So just remember the number next to x is always the slope, and the number by itself is the y-intercept. So here's how we'd write the equation. Notice that a on the calculator is the number next to x, so a is the slope. So I write a next to x, and then The B on the screen is the y-intercept. So I'm going to round it to 2 decimal places, and it'd be negative 5.73. You can see the x is written there, and you see the y has a little caret above it. That caret stands for predicted y. So we always include that caret when we make a least square regression line. Okay? But if you look in the red here, it says in statistics, we write the equation in context. So instead of writing the y and the x, we write the actual variables. So it's the predicted pieces of candy equals 2.57 times the houses visited minus 5.73. So this would be a correct equation written for AP Stats. And the caret, remember, on top represents predicted pieces of candy. And actually that little caret thing has a name. If we were reading this, we'd call it y hat. Okay, so the y is wearing a hat. But it stands for predicted y. Now, once we have our equation, we need to be able to interpret the values of the slope and the y-intercept in context. So I have the equation repeated here. Remember, the slope is the number next to the x variable. So interpreting the slope, the average increase in the y variable for every 1 unit of increase in x. If I was going to interpret the slope of our equation in the context of the Halloween kids, we'd say the slope is 2.57. Trick-or-treaters on average gain 2.57 pieces of candy per house they visited. Okay, so every time we visit one more house, according to the equation, I would add 2.57 pieces of candy to the bag. Now, can you actually get 2.57 pieces of candy from a house? No. But on average, that's how many pieces you would gain. Okay. Interpreting the y-intercept is the value of the y variable when the x is 0. So interpreting the y-intercept in our equation in context here, we'd say the y-intercept is negative 5.73. If the trick-or-treaters visited 0 houses, they would expect to have negative 5.73 pieces of candy. This does not make sense in context. Y-intercepts will often not make sense. Part of the problem in this situation is we don't have any data for what happens when you see 1 house or 2 houses or 3 houses. So when we make the least square regression line, the y-intercept ends up not making any sense, and that's fine. The equation will still work, okay? And we'll kind of explain later how we make sure that the equation will work. Now, making predictions. Let's use our least square regression line equation we found to predict how much candy we would get if we went to 40 houses. So here's my equation. I would replace houses visited with 40. And then I would simply solve that equation, and I'd get 97.07 pieces of candy. Okay, so if a trick-or-treater, visited 40 houses in this neighborhood, we'd expect them to get about 97 pieces of candy. Now, is that going to be exactly right? No, probably not, but it's a very good prediction. Okay, it allows us to have an idea of how much candy we would get. Now, cautions about these predictions that we're going to be making. We should never predict a response variable for an explanatory variable that is outside the domain of our data. Now, our houses visited data spans from 6 to 60. Like if we went back and looked at the table from the first page, the lowest number of houses we had data for was 6, and the highest number was 60. So we should not make predictions for any number of houses that are outside of these bounds. Okay, they cannot be considered accurate. And this is called extrapolation, when you predict outside the range of the data. You do not want to do that in AP Stats. Okay, and that's one reason why the y-intercept doesn't make sense, is because our data stopped at 6 houses. We don't have any data around 0. So it just shows you, we know at 0 houses you wouldn't have negative pieces of candy. That's why we wouldn't want to predict anything below 6 houses. Okay. So we do not want to extrapolate. Okay. No extrapolation allowed. Now, additional cautions. When making predictions, we are only allowed to predict the response variable in the equation, the y value. We are not allowed to substitute for the response variable and then solve for x. What I mean by that is you would not be allowed to say, hey, I got 200 pieces of candy. How many houses did I visit? We're not allowed to plug in values for y and then solve for x. Okay, we are not allowed to do that in regression. Okay, so that's super important. If you want to predict the explanatory variable from the response variable, we must make a new regression equation with the variable we want to predict as our response variable. So if I wanted to predict how many houses you visited by how much candy you collected, I would have to switch the x and y variable in the calculator. So I would make L2 be the x list, which would be how much candy I got. And then L1, the houses I visited, would be the y list. Okay? Then I would do the regression, and I'd get a completely new equation. So now I would be, if you look at the bottom here, now my equation would be predicted houses visited equals 0.36, that's the slope, times the pieces of candy I got plus 4.79. Now I could plug in how much candy I got, and I could predict how many houses I visited. Okay, so you got to be careful. You're only allowed to plug in values for x. Okay, now interesting thing to notice, the r value is the same as it was for our first equation. Notice it's 0.96. When we talked about correlation in the r value, remember, we said it didn't matter which variable was x and y, the correlation would be the same. This is a good demonstration of that. By switching the x and y variables, I still got the same correlation. My equation is completely different, okay, but the r value is the same.